All right, hello again. So hopefully you've seen the first video, and we're going to move on to the next part of it, where we were able to find what our initial population here is. This not so great number here. I'm going to use exact values with it, just so that way we have those. But then I'm going to go back and I'm going to put in approximations of them, so that way we know what that is as well. So let me go ahead and get rid of some of this previous stuff, and then we can move on. So essentially, what we have here is we have this exponential function, some a b to the x, where our exact value is going to be this bit of mess right here. But if I wanted to clean that up a little bit, I could approximate it. I could say that it's really some 68.657. So I have about that much bacterial culture when I begin. And then I'm growing by about 9.2% in there as well. So whichever is easier for you to kind of wrap your mind around. Again, for the purposes of the video, I just want to make sure that you can identify the pieces. That is, that this is what our initial is as soon as we started counting, and then this is our growth rate, where it needs to be greater than 1 in order to grow, right? If it's at 1, then it's going to stay the same amount it is. Anything greater than 1 means it's going to grow beyond it. Anything less than 1 means it's shrinking. So you could think of it as like 0.9 means it's 90% of whatever it was before, okay? So when we're looking at this, there are really only two types of questions they can ask us here. It can have to be something pertaining to time or something pertaining to the outputs. In this case, the output is how much bacteria culture we have. So this doubling period essentially means when are we going to get to, right, some 2a, right? So where if a is the 68.657, when do we get to double that? And the important thing here is that's when we're at double this population here. And now I'm going to be very careful in terms of our conceptual understanding. I'm going to use this kind of abbreviated piece of it, but I don't want to make so many abbreviations that it ends up causing a big issue now. So what I am going to do is I'm going to go back to what our original function is. So our f of x is some ab to the x, and hopefully kind of talk it out with you. So our doubling time is going to be where we have twice as much our initial population. If our initial population is some a, no matter what scenario we're talking about here, the doubling time will be twice that, or 2a. So in this case, all of these questions are, when they ask for the doubling time, essentially means, well, when is our exponential function a b to the x, when is that equal to a? Well, we can kind of walk through this situation a little bit, right? What we're going to have here is we're going to have this 137.31404 thing, right? What's written up here. But as soon as I divide this over, remember, this is twice as much what this amount is. So in the same way that I divide this a over here, what it'll do is it'll cancel out these a's, right? So if I divide this by a and I divide this by a, what we're left with is just some b to the x here, and then some 2 left over here. So once I divide that over here, right, so regardless of whatever's there, as soon as I divide this thing over, since it's its doubling time, I want to know, well, when does that growth factor get to 2? So that's one piece of it. The next is, well, what do you do with this? And essentially, the strategy is always the same, algebraically speaking, when we're going through this. Whenever you have a variable that's an exponent and you need to get rid of it, right? You don't have some knee-jerk reaction. It's like, oh, well, it must be this amount. The way you do it is you take a logarithm. And logarithms are a little tricky because sometimes you want to take a logarithm of a certain base Other times you just want to take the logarithm because then you can use all of your logarithmic properties. In this case, I don't care what log base I take. What I'm doing is I'm handling this x as the exponent here. So by taking the common logarithm, it makes it so I can still manipulate it fairly well. And one of our logarithmic properties is I can take any exponent here, or I can take, any exponent there, and then move it to the front of that logarithm. And that makes it a lot easier, right? If I'm trying to figure out what value x that is, well, now I can do that. I can just take this thing and divide it over. So I can divide, say, that over here. And you might find yourself in the situation in Desmos where you have your variable on the right-hand side. I can make this go x equal like this. And then I'll calculate that out for me, right? So, don't shy away from this input-output relationship. It's definitely something that's going to be helpful as we go through these videos. I think I'm going to keep going where I keep continuing on with it, but I'll see you in the next video.